We see your screen. Thanks, Michael.
Great. So, hi, I'm Michael McCartney. I'm at GE Aviation in Munich. And I'm going to be talking today about the main topic of my research, which is on improving the online prediction of combustion instabilities using machine learning, and specifically by combining the dynamic pressure information with what we already know about the system. So, like I said, the main research question is on whether we can leverage machine learning to combine the dynamic pressure information with our existing knowledge of the system. And I use the term practical systems here because I'm talking about state-of-the-art in terms of what's used in aircraft engines today. So to answer this question, we need to think about three things. So first of all is what the state-of-the-art currently is. Secondly, we need to think about what the dynamic pressure information adds to this. And then thirdly, how we can combine all of this to actually make predictions. So I'm going to give a little bit of outline on those three questions, and then talk about how in this project we've actually made predictions and the framework that we've set up to do so, as well as Bayesian neural networks, because that's a very useful tool for doing this that comes with all sorts of advantages that Ushnish alluded to on Monday, so I'll quickly go over those again. And then finally, I'll talk about the results of the work and some links to other projects and publications. So what is state-of-the-art in practical systems? So here you can see a lean premix combustor that's used in aviation engines. This is the GE TAPS combustor, and on the left you've got the compressor outlet, and on the right you've got the outlet of the combustor, and in the middle you've got the injector and where all the action happens, or the flame is burned. Now there's the main control for the engine is the fuel flow rate. This controls the amount of energy and power that you're putting into your system, and so you can use this to control whether the engine will accelerate or decelerate. And we also have a secondary control system in lean systems, which is the split between the pilot rich burn injector and the secondary lean burn injector. Now this is normally used, so the pilot operation is normally used for low power conditions, and then the secondary lean condition is used at higher power conditions where we can use the lean combustion to suppress emissions, lower temperatures and suppress emissions. So having this ability to split between the two fuel systems comes with a secondary benefit, which is that we can change the flow field around the injector while maintaining a constant fuel inlet and hence power output. And this means that when we get to an instability, when we're just using the secondary injector, we can activate the first injector, change the flow field and thus the flame response, and we can move away from the instability. So the use of the pilot injector gives us an extra degree of freedom that we can use in our control space to avoid instabilities, so that in operation we don't actually have to encounter them at all. But this does come at the cost of increased emissions, and we might not be operating at an optimum point. So additional to the control parameters, you've got some measurements. So you have the measurements at the compressor exit, and you have the core speed. And now you can see here that there's not very many measurements here. That's because measurement instrumentation is expensive and heavy, and the environment around the combustor is very hostile to measurements. So in practical systems, we're working with a very reduced set of instrumentation. And you'll see later on that means that the determination of the stability boundaries of our system has a certain amount of uncertainty. And so the question that we're trying to answer is whether adding the dynamic pressure information to this information can improve our predictions beyond just the operating parameters that I'll call all of these variables do alone. So then what does the dynamic pressure signal contain? Well, there's, like Ushnish alluded to, There's been a lot of research on this area. And the main things that have come out of this research are precursors to instability. So you've got things like intermittency, which are periodic bursts of periodic oscillations in amongst your stochastic signal. And then as Sarah was just showing, you can also see changes in the dynamics of the signal in the form of low order chaos. And there's numerous different measures for detecting these, like the 0 to 1 test for chaos she just presented. And there's also the Hurst exponent for detecting intermittency. But one of the things all of these measures have in common is the fact that they only look at the dynamic pressure signal in isolation. They don't look at the dynamic pressure signal in relation to the other parameters that we have to describe our system. And so that's a differentiator between the work that's been done and the work that we've been doing here. Another thing that's been shown by Ushnish is that there is a dependence of the spectrum on the operating condition, and that you can actually infer the operating condition from the spectrum. So he showed this on a simple burner, and he took the spectrogram of the turbulent noise and then used that to infer the equivalence ratio and the power of the system. So there's a lot of crossover between the information carried by the dynamic pressure signal and the operating parameters. And so we want to know whether there is some different information contained by the dynamic pressure signal that we can add to the existing information that we have. So in terms of how we can actually use this information, the expression at the top here is a way of combining all of our information together to make a prediction. So here, P of U at t plus delta t is the probability of being unstable at a time delta t in the future from our current time, which is t. And so we want to make these predictions given all the information on the right. So we make this prediction given where we want to be or where we expect to be in the operating space in the future, how far in the future that prediction is, where we are in the operating space now, and our current information about the pressure signal. So you can sort of see a schematic of this, a very simple demonstration shown in these two charts. So on the left-hand side, you can imagine a 2D operating space, and we're currently at operating point OPT. And we want to move to operating point OPT plus 1. So in 1 second in the future, we'll be at the second operating point. And this second operating point lies right in the middle of an instability zone. But then if we look at the plot on the right, then this will be the what P U of t plus delta t will be as a function of delta t. So when delta t is 0, where we are right now, there's a 0 probability of instability. And then as we get closer to our, or as we get further into the future, we'll see an increase in the probability of something happening, given the operating parameters and our current information. And the nice thing about this formulation is it means that we can evaluate multiple trajectories through our operating space. For example, we can keep our current information constant, so we keep OPT and our F of the pressure signal the same, and then we can vary where we expect to be in the future at a time delta t. So we can look at a candidate of different operating parameters in the future, and then we can use this framework to evaluate what the probability of being unstable at each of these different future conditions is. So to make these predictions, we use Bayesian neural networks. And so I know Ushnish went over these on Monday, but I wanted to quickly go over these again because they're very useful, especially in this context. So a Bayesian neural network is a neural network, but rather than having scalar values for your weights, you have distributions. Now this means that when you make a prediction, you also may have a distribution of your prediction. And so we've seen lots of work over the course of this project on Gaussian processes and why these uncertainties are useful, and I'll go into a bit more detail of why they're useful in this context later on. But the tricky thing about Bayesian neural networks is how you actually train them. So in this case, we used the approach proposed by Pierce and co-authors. And so I'll just quickly go over the training procedure here. So the first thing that we do is we take samples from our initial weights distributions. So these are prior distributions that are set up so that our predictions lie within our prior belief of the system. So in this case, we start with more or less no prior belief, so we expect our predictions to fall between 0 and 1. So we create a set of neural networks, and the weights of each of these are sampled from these prior distributions. Then we train these neural networks as individual neural networks, but when we train them, we include a regularization term in the loss function, which is shown here. And this regularization term anchors each of the parameters in our neural network to the prior distribution. And this was shown by Pierce and his co-authors that under certain conditions, it approximates to a Gaussian process. And once we've trained all of our neural networks, we ensemble them, so we average all the predictions, and then we end up with distributions over all the weights that are different from our prior distributions. And when we make a prediction, we have a distribution over our prediction, so we get a mean value and an uncertainty that goes with that prediction. So the data that I'll be presenting here is just based off the engine data that I've used. This was also done on some the annular rig data from Thomas and NTNU, which is in a paper, but don't have time to go through those results as well today. So the data that I'm presenting here is on 15 prototype aircraft engines. So each of these engines was ramped 4 times through an instability zone with slight variations in the control parameters controlling how they go through the operating space. So each of these 4 runs takes a slightly different route through the operating space and encounters the instability in a slightly different way. So then to split up the data, we had 5 engines for the training process, 5 engines for the validation or the hyperparameter tuning process, because although the Bayesian neural networks are easy to set up, they still have a few things that need to be tuned. And then we reserved the data from 5 of the engines for testing. So this data was completely unseen during the training and tuning process. And the results that you're about to see were all based on this data set. So first of all, we'll look at an evaluation of the predicted probabilities. So here you can see the log likelihood of the predicted probabilities. The log likelihood tells you the likelihood of observing your test data given the probabilities output by your model. So it gives you a measure of how good these probabilities are. And as you can see in the plot, the higher the number, the better. The absolute numbers are depend on the data set. So what we're really looking for is the relative difference between the runs. So you can see predictions made by 4 different models at different times into the future. So we're making predictions at different delta t's. So at 100 milliseconds in the future, all the way up to 1,000 milliseconds in the future. Now in blue, you can see a prediction made just using the operating parameters, and all the other colors are predictions made using the operating parameters plus some transformation of the pressure signal. So we didn't just pass the pressure signal directly to the machine learning, we did a transformation on it to reduce the number of dimensions and to extract some specific information from it. So the 3 transformations that you can see here are DFA, binary insta, which is a binary indication of instability, and the FFT, which is just the spectrogram. So I won't go into exactly what DFA is, but it's essentially a measure that's used to calculate the Hurst exponent, and it responds strongly to periodic behavior in the signal. And so if we go back to the graph, what you can see is that predictions made longer into the future, so at times larger than half a second, all the predictions converge to a similar value, and there's no improvement by adding the pressure information. But if you look at smaller time horizons, so at times lower than 400 milliseconds, you can see that all the models that are leveraging the pressure information do significantly better than just the operating parameters alone. Now, the green line, which is the model that uses a binary indication of instability, is sort of the minimal information model. So this is just an indicator of whether the system is currently stable or unstable. So you can see a lot of this advantage, or a lot of this improvement of performance, comes from just knowing whether the system is currently unstable and being able to avoid false positives, or obviously there's a correlation between if the system is currently unstable and whether it will be unstable in the next data point. But then you can see that the other models which have more information about the dynamics or the frequency response of the frequency spectrum of the signal add even more information, and they give you a better prediction. Now, in order to put this improvement of prediction into a more tangible form, we also evaluated the error of the predicted onset of instability. So here we're sort of simulating what it would be like to run these models on a test run as the test is running, and we make predictions into the future of whether we think the system will be unstable. And what you can see here in black is the predicted probability of instability from just just using the operating parameters. So this is a static prediction because it doesn't depend on any information coming back from the run. And so in the gray dashed line shows the prediction threshold. So we consider any predicted probability above this threshold to be a prediction of instability, and anything below this threshold to be a prediction of stability. And in red, you can see where the time where the system actually first went unstable. So if you look at where the black line crosses the gray line, you can see that the operating parameters model predicted that the system would go unstable significantly earlier than it did in reality. So now if you look at the blue parts, this is the prediction from our OP plus DFA model. So the blue dot indicates our current prediction, or our current position. So this is the time at which we're making this prediction. And then the blue line in shaded area shows the mean prediction and the confidence interval of that prediction. So we're predicting between 0.1 and 1 seconds into the future. And if we run this forwards, we can see how this prediction evolves as we go through the test. So I'll just pause it here. So you can see here that we're over 1 second away from the instability, and already the prediction made by the OP-DFA model is better than just using the operating parameters alone. So here we're predicting a lower probability of something happening in the next second. And that's because we've got access to this pressure information, and we're able to say it doesn't look like anything's going to happen soon, so we'll reduce the probabilities relative to just using the operating parameters. Then if we continue on a bit further, when we're 1 second away from the instability, the predictions now go above the prediction threshold. So we're now saying that the model thinks that the system will go unstable about 0.8 seconds in the future, which is closer to the real value than the operating predictions alone. So in this case, it seems like the system went unstable at a time later than was observed in the training data. And as we continue, this prediction more or less stays the same and becomes more accurate when we get even closer to the instability. So if we average a test done in this way, and we look at the error of the predicted onset, then we can see a similar trend to what we saw when we looked at the log likelihood, which is that as you get closer to an instability, so you're predicting, so the instability is occurring in the near future, the error of your predictions reduces. So you can see, again, in blue is the error of using the operating parameters as a function of the course speed used in this ramp. And again, below half a second away from the instability, the advantage of your models that leverage the pressure information comes through, and you start getting much better predictions relative to the operating parameters. And then when you're between 300 milliseconds and 100 milliseconds away from the instability, you're getting almost you've almost halved the error in the prediction time. So this is one of the main takeaways from this, is that when you're far away from the instability, the pressure information doesn't add anything at all, which is somewhat intuitive because over longer scales, we don't understand how the system moves through the space of the pressure data. But when you get really close to the instabilities, the pressure information adds a lot more information about the current state of the combustor and allows you to modify your predictions based off what's really being seen rather than what you've seen on average over all of your data sets. Finally, something that we didn't actually use in this study was the confidence intervals. And these are things that will require a bit more investigation in order to understand how they can be used fully, but we've just mentioned two ideas of how you can use them here. So one of the main uses of the confidence intervals is knowing when you're extrapolating versus interpolating. And so this is very useful, very important in the context of control, because we need to know when we can trust our predictions. So on the right here, you can see predictions made in distribution, and then predictions made where I've artificially moved the data out of the distribution and increased the amount of uncertainty in the prediction. So on the first chart, figure A, I have moved the operating parameters so that it's outside of the training data set. And in chart B, I've added some broadband noise onto the pressure signal so that it's so the machine learning is seeing a pressure signal that it's not seen before. And in both cases, you can see that the confidence interval increases, indicating that we're further away from our training distribution.
You have 2 more minutes, Michael. Perfect.
So the other way that you could use this is for fleet monitoring. So there's, as components wear and your engine ages, your instability zones could shift. This could be to degradation of components or coking of nozzles or something like that. And this would cause the noise signals that you'd see from the pressure signals that you see to change relative to your training domain. And so you could use the increase in the uncertainty as an indication that some engine might be requiring some predictive maintenance. Okay, so links to other ESR projects. Most of this work was done in collaboration with Ushnish and Professor Juniper, so I'm very thankful for their help. And then also as a work in progress that I wasn't able to present today, I've also been working with Nilam, Nils, Louise, and Sagar on using identifications for input-dependent finite impulse response components, but I'll have to talk about that at a different time. So thank you very much.
Thank you, Michael,
Thank you.
for your very interesting presentation.